In this video, we'll discuss ancient Babylonian mathematics. Now, when we look at the beginnings of mathematics, one of the reasons it starts to take off is due to the agricultural revolution that was occurring around major river valleys around the world. And part of that is because to make the revolution occur, it required different forms of mathematics, and to keep track of that mathematics, written language had to be constructed. Now, you might ask, well, why would mathematics and language be needed? But think about what it is that's needed to truly make agriculture occur. We need different forms of engineering to help make sure that the crops can grow and can be constrained, especially due to things like flooding of these major rivers. Once you have significant components to your crops, you need to keep track of what it is that you have and how do you buy and sell it, both within your society and with other societies. As you want to improve your crop production, you start to use other tools and resources and using science to help you with that, which led to the construction of the Bronze Age as well as the Iron Age and the use of those different types of tools. And with that comes the production of societies and cities. We move from a nomadic hunting and gathering communities to now larger cities that then allow for that agriculture to be supporting. And that led to marketplaces for the buying and selling of crops and meat. And that also led to opportunities for leisure for upper class citizens. And leisure is where we start to see the scientific and mathematical discoveries occur for the next several millennia. So it's important that the revolution occurs to help build societies that then support mathematical and scientific discoveries. Well, one of those societies was ancient Babylon. And we are able to learn more about the Babylonian culture due to all the clay tablets that have been found over the years. Currently, there's about 500,000 clay tablets that have been found that go back as far as 2100 BCE. Of those, only 400 relate directly to mathematics, and about half of those are only mathematical tables. Now, when we look at the Babylonian system, they used a base 60 system written in cuneiform. And we began to decipher what that cuneiform stated in the 1800s. So it's only been about 200 years that we've been able to read much of the Babylonian tablets. So if we want to convert a base 60 number to base 10, the first thing we're going to do is we're going to use some other type of notation so that we don't have to learn how to write cuneiform. Instead, we're going to use our numbers, and we're going to use commas to separate place values and a semicolon to separate our decimal point. We then will multiply each place value by its corresponding power of 60. And just remember that if it's a decimal, it's raised to 60 to some negative exponent. So if I had the number 2, 50, 35, semicolon 15, 30 in base 60, and I want to convert that to base 10, I'm going to follow my place values one at a time. So if I look, this is 2 times 60 to the second, 50 times 60 to the first, and 35 times 60 to the 0th. That's why it's times 1. And then the semicolon tells me I'm now going into fractions. So this becomes 15 times 60th to the negative 1 and 30th times 60 to the negative 2. And I'm going to write those in fraction form, not decimals, because they could handle fractions. So that's 7,200 plus 3,000 plus 35 plus 1/4 plus 1/20th. And then if I simplify that, that becomes 10,235 and 31 120ths. That will be my conversion over to base 10. And again, I want to leave it in that fraction form. Now, the Babylonians were able to discover many different forms of mathematics, especially in geometry and in algebra. Within geometry, they often used the value of 3 for pi, and they eventually converted that to 3 1/8, which is even closer to the irrational value of pi. With that, they were able to determine that the circumference of a circle would be 3 times the diameter, so pi times the diameter, and then they looked at the area of a circle and said that it was the 1/12 times the circumference squared. And if you actually go through it and simplify that, that will come to 3 times the radius squared, or pi times the radius squared. Additionally, they were able to utilize the Pythagorean theorem over 1,000 years before Pythagoras is credited for it and the Greeks. Additionally, they could calculate the volume of solids if the area of the base was provided. Now, within algebra, they could solve many different forms of equations. They could do variables up to the fourth degree, systems of equations, and even calculate square roots such as square root of 2 up to 5 decimal places. They also could use law of signs within their multiplication. And if you look at this tablet, this is representing the concept of this square root of 2. So there's a lot of mathematics that we think of that we know and we utilize within our courses and our classes that becomes known and discovered thanks to societies like the Babylonians. Now let's look at an example of a systems of equation problems that comes from one of their ancient tablets called BM 13901, which is from the British Museum. In this, it translates approximately to say that the sum of the areas of two squares is 1,525. The side of the second square is 5 more than 2/3 that of the first. Determine the side lengths of each square. What I do first, just so I can visualize what's happening, is I draw to the two squares and I label their sides. I don't know the length of each side, so I'm going to give this an x. And I know it's length times width, so that's x squared. For the second square, I'm going to use y, and I know that would be y times y gives me y squared for its area. Now I can utilize my information here to help me create my two equations. The first one, the sum of the areas of the two squares is 1,525. So I have the area plus the area will equal 1,525. My second statement, the side of the second square is 5 more than 2/3 that of the first. So the side of my second equals 5 plus 2/3 of x, because that's the more than. Now I have two equations. I can solve my systems of equations, which is something the Babylonians could do. And what they would do is they would substitute this value in for y squared, and then they would expand that. But their goal was to get it in a certain form. And that form would be x squared plus bx equals c. And that's 1x squared. That's important. So let's expand this out, and then let's simplify. And we're going to move the 25 to the right-hand side. So this becomes 13/9 x squared plus 20/3 x equals 1,500. And the Babylonians could handle fractions, so there's no reason to convert this either. But I do need to get this to 1x squared. So I'm going to multiply the entire equation by 9/13. In doing so, this will end up with x squared plus 60/13 x equals 13,513. Now, once I have it in this form, the Babylonians would use a form of the quadratic formula. Again, they like their tables and their formulas. So that form would be negative b over 2 plus the square root of b over 2 squared plus c. Very similar to our quadratic formula that we use. So let's substitute in the values we have. Then once we have them in there, we can simplify each of those values, and that becomes negative 30/13 plus 420/13. And when I add them together, that becomes a value of 30. So that one length of the square has to be a length of 30. Now that I have its value, I can substitute into either equation and then find the value of y. So let's just do it for the second equation. So 5 plus 2/3 of 30 gives us 25. This means that the length of one side of the square is 30 and the other is 25.